Hello students, good morning and welcome. Myself Dr. D.M. Chavan, Assistant Professor in Chemistry, Indira Mahavidyalaya, District Yavatmal. Today we discuss heterocyclic compounds. Dear students, what is meant by heterocyclic compound? Heterocyclic compounds is nothing but cyclic compounds which contains the one or more heteroatoms along with the carbon in the cyclic ring. The heteroatoms present in the heterocyclic compounds are nitrogen, oxygen, selenium, phosphorus, silicon, boron in the ring along with the carbon. These atoms are known as heteroatoms because these are present other than the carbon in the cyclic ring. The word heterocyclic is derived from the Greek word that is heteros meaning different. More than half of the compounds or organic compounds known to the human beings are heterocycles. These heterocyclic compounds are present in the drugs, vitamins, and natural products are nothing but the heterocyclic compounds. The simple example of the heterocyclic compound is the pyrrole. Along with the pyrrole, there are other examples of heterocyclic compounds, that is furan. It contains the oxygen as a heteroatom. Then thiophene. This thiophene contains the sulfur as a heteroatom. Then pyridine. It contains nitrogen as heteroatom. Quinoline, indole. These are the various heterocyclic compounds. In these heterocyclic compounds, there is the heteroatoms present in the cyclic ring along with the nitrogen atoms. Now we discuss in detail the pyrrole. The IPC name of the pyrrole is the azacyclopenta-2,4-diene. These pyrrole have the two double bond in the cyclic ring and one nitrogen atom. Nitrogen in the Greek word is known as aza, therefore its name, that is IPC name, is azacyclopenta-2,4-diene. It is the nitrogen containing 5-membered heterocycles. These pyrrole present in the important natural products are biochemicals, that is chlorophyll, hemoglobin. Hemoglobin contains the pyrrole as a nucleus. It occurs in coal tar and bone oil. Now, what are the methods of synthesis of pyrrole? There are three important methods of synthesis of pyrrole. First method is from acetylene. When two molecules of acetylene and one molecule of ammonia are passed through the red hot iron tube, then there is the formation of pyrrole. The pyrrole can be formed from the acetylene and ammonia by the reactions between ammonia and acetylene. It gives formation of pyrrole along with the elimination of H2 gas. Then another method of synthesis of pyrrole is from succinamide. This is the succinamide. Succinamide first undergo the enolization. This is the enol form of succinamide, and this enol form of succinamide on dry distillation in presence of zinc dust, it gives the formation of pyrrole. Then third method of synthesis of pyrrole is from the furan. Pyrrole can be synthesized by passing mixture of furan, ammonia and steam over a heated alumina. Suppose this is the furan. Then furan, ammonia and steam, if they are passed over the heated alumina, it gives the formation of pyrrole along with the elimination of the water molecule. Now, what are the physical properties of pyrrole? It is colorless liquid. Its boiling point is 404 Kelvin. It is sparingly soluble in water but readily soluble in alcohol and ether. It rapidly darkens on exposure to air because there is air oxidation of this pyrrole. These are the various physical properties of the pyrrole. Now we discuss the molecular orbital structure of pyrrole. In pyrrole, nitrogen and carbon atoms, they are present in the sp2 state of hybridization. The sp2 hybrid orbitals of nitrogen and sp2 hybrid orbital of the carbon, they overlap and form the sp2 sigma bond. Similarly, the sp2 hybrid orbitals of this carbon and s orbitals of hydrogen form the sp2s sigma bond, and all the carbon atoms with the adjacent carbon atoms sp2 hybrid orbitals, they overlap and form the sp2 sigma bond, sp2s sigma bond with hydrogen, and there is the formation of the sigma skeleton. This is the representation of the sigma bond skeleton of the pyrrole. This is nitrogen carbon sigma bond, this is carbon hydrogen sigma bond, and this is carbon carbon sigma bond. This is the molecular orbital structure of pyrrole, this sigma bond skeleton. Now to discuss the pi skeleton of pyrrole. We know that the carbon atom and nitrogen atoms, they are present in the sp2 state of hybridization. After overlapping of the sp2 hybrid orbital with the adjacent carbon and with the hydrogen, the one unhybridized p orbitals in the carbon having one unpaired electron, they are present parallel to each other, and each p orbital contains the one unpaired electron. They overlap laterally, and there is the formation of the pi skeleton of the pyrrole. This is the lone pair of electrons present on the nitrogen atom unhybridized p orbitals, and this is the unpaired electrons present in the unhybridized p orbital of the carbon. All these p orbitals on each carbon atoms, they overlap laterally, and there is the formation of the pi bond, and it forms the pi skeleton of the pyrrole. This is the electron cloud above the plane and below the plane of the ring. Because in the sp2 state of hybridization, there is the planar geometry, triangular planar geometry, and the electron cloud present above the plane of the ring and below the plane of the ring. This is the pi molecular orbital containing electron. This is the simple representation of the pi molecular orbitals of the pyrrole. Then we discuss the resonance structure of pyrrole. As we know that the lone pair of electrons present on the nitrogen, they are parallel to the unhybridized p orbitals of the carbon atoms present on the pyrrole, and the lone pair of electrons present on the nitrogen, they undergo the resonance stabilization, produces the following resonating structure. This is the resonating structure of the pyrrole. This is the resonance delocalization of pyrrole. Now we discuss the basic nature of pyrrole. Dear students, we know that the nitrogen atoms present in the pyrrole have the lone pair of electrons, and that lone pair of electrons are responsible for the basicity. Though this pyrrole is a base, but it is a big base, because the lone pair involved, we are already discussed earlier, the resonance delocalization of pyrrole. Due to the involvement of the lone pair of electron in the resonance delocalization, it is a big base, because they are not easily available for the donation to the acid. and this resonance delocalization decreases the basicity of the Pyrrole. This is the Pyrrole ring, and this is the nitrogen lone pair of electrons, and this lone pair of electrons are involved in the resonance delocalization, and these are continuously along in the motion, and they are not readily available for the donation, as we know that the lone pair donors are base, though the nitrogen atoms have lone pair of electrons, but they are not easily available for the donation. Therefore, this Pyrrole as a weak base, because the lone pair of electrons are continuously revolving in the ring, and they are not easily available for the donation. Therefore, Pyrrole is a big base. Thank you, dear students. Thank you for watching my video.